Hi, I'm Brian Getz. I'm Java Language Architect at Oracle, and today we're going to be talking about the new language and core library features in Java SE8. Java 8 has been under development for nearly 4 years. We started on the Java 8 language features well before we launched Java 7. The key new feature of Java 8 is, as most of you probably know, Lambda expressions. And this is a feature that Java developers have been waiting for quite a long time. So I'm pleased to finally be able to say that it's finally here, and I think you're going to be happy with the results. Java 8 is, quite literally, the largest upgrade to the Java programming model we've ever done, larger than generics. And while it may involve a small number of features, Lambda expressions, interface evolution via default methods, and data parallel operation support for collections, when you take them together, this represents a coordinated co-evolution of the Java programming model spanning across the VM, the language, and the core libraries. And we've done this while maintaining our overarching commitment to compatibility. So we didn't just nail things on the side here, and people commonly ask, gee, why did it take so long to do this? And the answer is, it was making sure it was not nailed on the side is what takes most of the time. So let's start from the top with the primary new feature, Lambda expressions. So you may be familiar with Lambda expressions if you program in JavaScript or in Ruby or in Python or a number of other languages. It's basically a simple way to express code that can be passed around as data. Now, Java has always given us good tools for abstracting over data, such as classes, interfaces, inheritance, generics. But what's been missing is a good mechanism for abstracting over behavior. And this, in turn, affects the way we program for the worse. So let's take a look at some examples. So as a simple example of what I mean, take a really simple problem like, I've got a collection of people, and I want to remove all the people who are over 18. Now, the way we've always done this is you write a loop. You loop over the elements, you test them, and you remove the ones that match the criteria. So here's code that looks like how we would typically do this. But what you'll notice is every time you write code like this, you have to duplicate the boilerplate of iterating over the collection, getting an iterator, removing the element, and the only thing that might change from instance to instance is actually the criteria that you want to use to remove elements from the collection. And so this is a little bit of reinventing the wheel, and we've had to do this because this has been our only option, but there's a better way. So the better way involves identifying that what we're really doing is abstracting over some behavior. There exists some criteria for removal from the collection, and what we want to do is remove all the elements that meet that criteria. And we could do this today. We would use the tools that we have. We would model the criteria with an interface like predicate, and then we would create a method that says, remove all the elements from the collection that match that predicate. And so far, so good. We only have to write this removal loop once, and that's an improvement. But we've got a problem where the rubber meets the road. When the user has to actually write the code to do this, it gets pretty ugly because the only tool that we've had for representing a little bit of behavior that we want to model our criteria is inner classes. So when we try to use this new method to replace the loop on the earlier slide, the code is more abstract, but it's not really any smaller or more readable because of all of the syntactic noise associated with inner classes. And this code here is pretty ugly. And so since we don't like to write ugly code, we end up not writing libraries like this in Java as it stands today. But the key thing to realize is the ugliness of inner classes is mostly accidental. There's an awful lot of unnecessary syntactic goop. And if you look at it this way, all of the stuff in gray is really unnecessary. The essential stuff is the stuff in black. We have a criteria that takes a person and returns whether or not that person is over 18 or not. So Lambda expressions are designed to get us out of this mess. The inner class instance that we were passing to remove all represents a little bit of behavior that we want to pass into the removal method. And what we can do is replace the more cumbersome inner class instance with a Lambda expression that means the same thing. So here's what this code looks like using a Lambda expression. It's exactly the same code. We're basically saying, remove all the people from the collection whose age is over 18. And the code that we've written here for the lambda expression is basically an anonymous method. We've compressed away all the syntactic overhead, but it's basically a method. It has an argument list and a body and a return type and all the same things that other methods have, just without all the syntactic overhead. So at the simplest level, what lambda expressions do is they reduce the syntactic overhead of behavior as data. So the client code for calling this method definitely gets a lot less painful. It's actually a lot more deep than just syntax. For one thing, the implementation isn't just inner classes, and this opens the door to all sorts of performance improvements over doing things with inner classes. But the real win is how it makes a qualitative difference in the way we program. When inner classes were our only tool for abstracting over behavior, it would make us shy away from writing APIs like the example we saw because using them would just be too painful. But with lambda expressions, using them isn't painful, and that means we're more willing to write APIs like this, which in turn results in better code being more readable, less error-prone, more maintainable. So the remove all example is just a simple example. Most of the code we write every day is expressing aggregate operations over a collection. You could think of that as expressing queries over the collection. So as a simple example, imagine we have a collection of people, and we want to pick out the weight of the heaviest man in the collection. The way we would do that today is with a for loop, as shown here. But we can also express this using a more abstract approach, using more general tools for selecting, transforming, and aggregating, where you can kind of fill in the blanks with lambda expressions to describe the behavior you want. And so here is another way to express an answer to the same problem. We're saying, take the people in our collection, select the ones who are men, for each one, map those to their weight, and then take the maximum value of all of those weights. And the result is much more clean, readable code. And it may look like this code is not very efficient because you're doing three different things. This code is actually quite efficient because the library is going to fuse these three operations together into a single pass. So we could have written libraries like this using inner classes, but that would have been silly because no one was going to be willing to use them with inner classes. But once we clear away the syntactic noise of inner classes, it becomes obvious that this is a cleaner way to express the problem at a higher level of abstraction. And the code is more readable because it focuses on the what of the problem we're solving rather than on the how of how to solve it. That means it's also more likely to be correct, as the code is really just about the problem being solved rather than the low-level details of solving it, which makes it easier to spot when the code isn't doing what you intended. Readable code is maintainable code. So something really interesting happened when we converted the code from the for loop to the aggregate operation. Not only did we raise the level of abstraction of how we represent the code, but we've also inverted the control of the computation. So in the for loop version, the client code is directly involved in controlling the computation at every step of the way. It gets an iterator for the collection, and then in every loop iteration, it asks the iterator for the next element. In the streams version, the library is actually in control. The client loads up the library with all the stuff it needs. Here's your filtering criterion, here's your mapping criterion, here's your aggregation behavior, and now go. And the library just runs from there. This frees up the library to use techniques like laziness or out-of-order execution or parallelism to get the job done faster without the client having to be involved in these things. So to zoom in on one of these benefits, parallelism, Java has always had good support for parallelism. We've had support for concurrency from day one, and we added a powerful fork join library in Java SE7. Now, fork join is a really efficient library for executing parallel algorithms, but converting an algorithm from serial to parallel has always been a big leap. And if it's a lot of work to do, because we're all lazy, we might not do it as readily. It also makes our code look very different. So to give you an example, this is what the maximum weight example looks like using fork join. The red code is the business logic having to do with people and weights and aggregation, and the black code is mostly boilerplate just to feed the computation. So as you can see, the sequential and parallel versions of the same code look really different, and that's a big pain point for us to go parallel. Now, coincidentally, or actually not, lambdas are also a key driver to developing parallel libraries. The inversion of control we just talked about frees up the library to go parallel without rewriting the code. So instead of the client asking the collection for the next element and operating on it in every loop iteration, the client can say to the library, here, do this for every element. And that is something that can be parallelized much more easily. So going back to what our stream code looks like, in order to make it parallel, all we need to do is change the stream declaration. And instead of saying, give me a stream of people, we say, give me a stream of people that operates in parallel. And all the rest of the code is exactly the same. So the parallelism is explicit. We're not magically adding parallelism to code that doesn't look parallel, but it's unobtrusive. The code is still more focused on the business logic and leaves the parallel mechanics to the library. Now, this may be a trivial example, and the for loop example actually doesn't look so bad either, but as we scale up the sorts of programming on collections that we do every day, the power of this approach really starts to show. So here's an example of some typical business logic that we write every day. You're groveling over some collection, you're extracting the desired information, and you're printing out some summary of it. Now, if you look at this code for just a few seconds, and I asked you what it did, you probably have a hard time answering because there's enough detail here that you actually have to read through the whole thing. And code that's hard to read is going to be more likely to be wrong than code that's easy to read. So what this code does is it takes transactions where the buyer is over 65. For each of those, gets the corresponding sellers, and then sorts the sellers by name and prints them. Now, if we rewrite this code using the new stream libraries in Java 8, not only does the code get shorter, but it's a lot easier to tell what's going on because the code reads a lot more like the problem statement and isn't overwhelmed by all the implementation details. And this really illustrates the key value of the entire effort of adding lambdas to Java. It's enabling us to write clearer, more maintainable, less error-prone code. If you look at this code, it's much easier to see what's going on. You're saying, take the transactions, filter them to select the ones where the buyer is over 65. For each of those, get the seller, toss away the duplicates, sort those by name, print them out. Very clear, very readable. Okay, so turning to our other big feature for Java SE8, you may have noticed in the previous examples that we were using a method on collection called stream, and collection hasn't historically had a method called stream. So this is where default methods come in. Default methods provide us a way of evolving interfaces over time. And this is really critical because otherwise we couldn't have added the features that we've shown so far to collections. And then we would have been facing a choice of either use the old collections you know and love or use the new Lambda features but not both. And that would have been a terrible choice. So what default methods let you do is add methods to interfaces over time so that we can evolve our interfaces over time. And that way, we're not faced with the situation of having to replace aging libraries because they're no longer able to do what we need them to do. So going back to our previous example, we had this new method on collection called stream. So how did we add this? And what happens if you invoke the stream method on some old implementation of collection that didn't know about stream? Well, the answer is that stream is a default method. A default method in an interface is one that provides an implementation. And that means that subclasses that don't override the method would just inherit the default implementation from the interface. So we added a few default methods like stream, parallel stream, and for each to enable existing collection classes to use lambdas. So as you can see, declaring a default method is really simple. You declare the method as being a default method, and you provide a body. And that's it. And from the outside of the interface, the users can't tell the difference. They're fully virtual methods. Subclasses can override them or not. And from the perspective of the client, they're just ordinary interface methods. So this is a way of inheriting behavior not only from superclasses, but also possibly from super interfaces. And this gives us a path to evolving interfaces like collection, list, set, map over time to add new features as it makes sense. Okay, so wrapping up, we've seen a brief tour of the major new language and library features in Java SE8. Now, the number of features may be small, Lambda expressions, default methods, aggregate operations on collections. But together, they're going to have a big impact on the way we program. And we've taken great pains to integrate these features into Java in a way that preserves the feel of Java. So go ahead, download Java 8, give it a try. And for more information, check out these resources.